total wave function is going to be a spatial part times a spin part. We know all the interactions in the system, and we know we've got to account for indistinguishable electrons, and that the total wave function has to be antisymmetric, that is change sign, when we exchange the two particles, right? And if we have our helium atom in its ground state, right, that's a 1s squared configuration. So we know how to, we've taken a look at writing the spatial part. What about the spin part? What do we know about the spin? Well, right, the electrons, we can't write a function for the spin in terms of the coordinates. We just have these. We know that all electrons are spin 1/2, and then that means we can either have an m sub s of plus 1/2 or an m sub s of minus 1/2, right? And we talk about that as being spin up or spin down, so we might represent it by an arrow, or let's just name the function, right? Let's call this the alpha state, and we'll call that the beta state, right? How can we put them together? Well, S, spin, right? Spin represents an intrinsic magnetic moment of the electron. It's a vector quantity. And that's important because there are only certain ways that we can add spins together. They have to obey the vector rules. And so when we make the total spin of the atom, we'll add the individual spins of the two electrons, lowercase and uppercase, right? This is for the atom in total, and these were the individual electrons here. And when we add those two together, we can do this in two ways. We can either add two that have the same spin and get a total spin of 1, or we can add them against each other. That is, we subtract one from the other, and we get a total spin of 0, right? But what else do we know? Oh, if we have S of 0, there's only one m sub s value. That'll be 0. But if we have an S of 1, then we can get m sub s values of 0 plus or minus 1. Right? So there are 3 m sub s values associated with coupling them together in the same direction, and only 1 m sub s value associated with coupling them paired. So if we take 2 electrons, how can we put together these alpha and beta states? Well, let's take a look at this, right? We could put both up. We could put both down. Oh, that's easy. That must correspond to an S of 1 and an m sub s of 1, and this would correspond to an S of 1 and an m sub s of minus 1. Or we could take 1 electron, put it up, and 1 electron, put it down. But we don't know which one is electron 1 and which one's electron 2. So at the same time, that could be, we have to allow for the possibility that we've switched them. And if we're going to do that, there are 2 ways we can put them together. We can either put them together where we add them, or we can put them together where we subtract them. All right? And if we want to keep things normalized, hit that with a normalization constant of 1 over the square root of 2. What do they correspond to in terms of the S and m sub s values? When we add the 2 together, that's equal to an S equals 1 and an m sub s of 0. When we subtracted the 2, that's equal to an S of 0 and an m sub s of 0. Now notice something else, that if we interchange electrons 1 and 2, this one stays the same. So under exchange, this first function is symmetric. This one, again, it looks exactly the same. If we do that, it's also symmetric. The wave function does not, that combination of spin wave functions does not change sign if we exchange the two. Over here, with the plus sign, doesn't matter, order of operations is not important for plus. Oh, again, this would be symmetric. But here, if we switch, exchange 1 and 2, we will change sign. So this is antisymmetric with respect to exchange. Think about that now. When we go to make the helium atom ground state, right? We know how we have to write the spatial part. Now we have to multiply it by the appropriate spin part. And we have to make sure that the total wave function is antisymmetric with respect to exchange. So now we're going to have a wave function that looks like we're going to take the 1s wave functions for both electron 1 and electron 2. We'll multiply those together. That gives us a symmetric with respect to exchange spatial part. But the total wave function has to be antisymmetric, and therefore we're going to have to multiply by the, we would have to multiply by this 1 over the square root of 2 minus combination. And now we have an antisymmetric spin part coupled, multiplied by a symmetric spatial part, gives us a total wave function that's antisymmetric. That's always what we need to do. We need to, there's one and only one way we can write the ground state to get this overall antisymmetric wave function. Now let's take a look at the excited state.